Hello and welcome back. In this video, we will further our discussions of fluid statics. Just to summarize what we've done so far, we introduced pressure as force divided by area, units of newtons per meter squared or a Pascal. Three different types of pressure. Gauge pressure is the pressure an object experiences when it is submerged in an additional fluid, where this is the density of that fluid that it's additionally submerged in, additional to the atmosphere. The atmospheric pressure is already given to us as this value here. But the gauge pressure, the density of whatever fluid the object is further submerged in, acceleration due to Earth's gravity times how deeply the point is submerged, or the object is submerged. The atmospheric pressure is 1.013 times 10 to the 5th pascals. This is the pressure at sea level dry air, and that's the atmospheric pressure we will use. And then the absolute pressure is just the sum of those two pressures. We introduce the density formula. Density gets the symbol rho, and it's mass per unit volume. And then in the last video, or two videos ago, we derived the buoyant force equation. This is the force that is exerted up on an object due to the fact that it is submerged in a fluid. And in the last video, we were able to see that this is just equal to the weight of displaced fluid. So this is the weight of the fluid that had to move out of the way in order for the object to be in the fluid. So now let's pick up from there and see what kind of a relationship we can find between the volume of the object that's submerged and its total volume and the density of the fluid and the density of the object. So let's say we have a vat that has some kind of fluid in it. So there's the density of the fluid. And we have an object that is partially submerged. So we'll say that this is our object. And let's make this the V submerged. So this is going to be V submerged. And this volume up here, which I will polka dot, this is V not submerged. So that's the part of the volume of the object that's not submerged. Okay? Now the object has a density as well. So let's use the symbol rho naught for the density of the object. And let's use the symbol, of course, rho sub F, density of the fluid. And let's draw a free body diagram for this object. So here is the object turned into a dot. What forces are acting on it? Well, the Earth is pulling on it. And the Earth is pulling on the entire mass of the object. So this is going to be the mass of the object times the acceleration due to Earth's gravity. So MO is just going to be mass of entire object. The Earth pulls on all of the mass, all of the molecules that make up this object. So mass of the object times the acceleration due to Earth's gravity is the force downward. Well, why is the object in static equilibrium? Well, because there's a force upward on it, and that's called the buoyant force, and that's due to the fact that it is submerged, or not submerged, but partially submerged in a fluid. So there's the buoyant force. Okay? So now what is the buoyant force equal to? Well, remember, the buoyant force is equal to the density of the fluid times the acceleration due to Earth's gravity times how much of the object is submerged. So this is the volume submerged. This mass of the object, MO, can be written as the density of the object times the volume of the object. And that's just rearranging this formula to solve for mass. I just multiply by volume on both sides, so I can re-express the mass of the object as the density of the object times the volume of the object. So notice that VO is the volume of entire object. So all the little subscripts O are keeping track of the entire object's properties, and we're using sub and non-sub for only parts of the object. All right, so I can write this then as re-expressing for mass, density of the object, volume of the object times the acceleration due to Earth's gravity. Now this object is in static equilibrium. These are the only two forces acting on it. Therefore, they must be equal to one another for the object to be in static equilibrium. So I can set them equal to one another. So the buoyant force is equal to mog, and this is because object is in equilibrium. Forces have to be balanced. Forces up must balance forces down. All right, so let's go ahead and plug in the buoyant force for the left-hand side of the equation, and then we'll plug in also for the right side of the equation. What do we come up with? Well, we're going to have the density of the fluid times the acceleration due to its gravity times the volume submerged. So that's re-expressing the buoyant force as what it is equal to here, is equal to the mass of the object times the acceleration due to Earth's gravity, but we're going to re-express the mass of the object as the density of the object times the volume of the object times the acceleration due to Earth's gravity. So there is Newton's second law now written, re-expressed in terms of densities and volumes. Notice that little g, the acceleration due to Earth's gravity, is on both sides of the equation, so it can be canceled out. And we're just going to rearrange a little bit and see that the volume of the object that is submerged to its total volume, so this is going to be the fraction submerged, is equal to the density of the object to the density of the fluid. The ratio of the density of the object to the density of the fluid. So I can predict how much volume, what percentage or what fraction of an object's volume will be underneath the surface if I know the density of the object and the density of the fluid that that object is going to be partially submerged in. So notice that for ice, for example, floating in water, the density of ice is equal to 900 kilograms per meter cubed, and the density of water is equal to 1,000 kilograms per meter cubed. Therefore, the ratio of the density of ice to the density of water is 900 to 1,000, or 9/10. So that means 9/10 will be the ratio of the volume of the submerged part of the ice, so this is submerged ice, to the total volume of the ice, will be equal to 9/10. As an example, so 9/10 of your ice cube's volume will always be below the surface. And so when the ice starts to melt, this ice cube will shift up a little bit to always keep 10% above the surface and 90% below the surface because of the density ratio of the ice's density to the fluid's density. So this is a very cool, important, interesting formula that we will be able to now include in our toolbox as we move along. And of course, you don't have to memorize that. It all comes back to just looking at a free body diagram for an object floating in a fluid and using the density formula to re-express mass as density times volume, and writing down Newton's second law. So it's tools that we already have in our toolbox. So it's not something new that we need to memorize, but we can always drive it as needed. So this now adds to our knowledge of fluid statics, and we will work some problems applying these concepts in the next video. Thank you.